So just accept that. All right, so welcome to F1TENTH. This is a course that's going to teach you how to drive autonomous cars and then how to race autonomous cars. And today we're going to go through what you're going to cover throughout the semester. So I'm going to give you like Instagram snapshots essentially of what's going to be lecture by lecture and all the awesome and fun stuff you're going to learn and all the experiments you're going to run through that, right? So in the beginning, we'll go through all the admin trivia. That's essentially the logistics, grading criteria, the policies, and then we'll go through the course support as to who our instruction team is, what you can find on Canvas, Piazza, GitHub, and then what our expectations are. Right, this is a graduate level course, but the course is pretty broad in terms of what it needs. And so it's important to have, the right expectations, not less than that, not more than that. And then we'll start with a brief introduction of, this autonomous racing cars. At any point, please feel free to interrupt. I mean, this is your class. It's nice that we actually have a small class. Ideally, we would like to have many more students, but since it's a smallish class of about 25 people, you'll get to know each other well, you'll be working together a lot. And essentially our goal this semester is to help you learn how to build, code, and then race these autonomous vehicles. And these are essentially scaled down versions of 1/10 scale Formula One type racing cars. But it's 10 times the fun because you get to actually do all of this, hands-on, right? And you get to essentially work with this system that's complex. It's not too complex. It's not too simplified. And what we have done is we've put together these race cars from the chassis and the power management system, integrated all these sensors and interfaced them to a NVIDIA GPU board. That's the NVIDIA Jetson NX board. And that runs, and what you will build is essentially the autonomous vehicle software stack for perception, planning, and control. And then this will allow you to do a lot of very fun projects. And many people have used these platforms to look at different autonomous vehicle and autonomous systems projects overall. There are many things that this platform is capable of. I've just put a collage of things here, like, obstacle avoidance things, model predictive control, people, driving manually and training the vehicle to drive as well or as badly as they do. And then the vehicle through imitation learning or behavioral cloning can actually realize the same behaviors, right? And then vehicle to vehicle collaborations have been, there's just experiments that people have been able to do using these platforms. On the perception side, there's, doing basic like classic computer vision for lane detection, lane keeping assistance, computer vision approaches using optical flow for, navigation. And then there are different visualizations that you'll learn to use. And then different, localization and mapping packages. All of these run natively on this platform. And what we have essentially done is we've done all the kind of the groundwork to make sure that this platform runs efficiently. The code that you get as, the starter codes for all the work that you will do is clean, it's documented, it's tested out. So you're not hung up on, this platform specific kind of, nitty gritty stuff, but you are really focused on that you learn the concepts and then you put the concepts to work on this platform, right? So we have a variety of simulators and essentially these simulators can help you go from driving in the real world to capturing snapshots in the real world. This is one of our very old simulators. And now, we have much more simulators, which I'll show you as we go through the course. But essentially, our idea is to bridge this sim to real gap. That can I do most of my work in simulation and do it rapidly and programmatically, and then, adjust for the reality as I drive in the real world. And so can I reduce, say, this development time, and more importantly, the development frustration of not just working in the physical world, but keep moving, iterating between the simulator, the real world, coming back to simulation, tweaking the algorithm, going back to the real world. This has also been used for, like, profiling hardware in terms of, like, how do I have, CPU centric or GPU centric algorithms, and how does that affect performance? And then folks have looked at it for testing and verification. But that's just to show you, okay, this platform is capable of doing stuff and people have done stuff with it. But first, let's go through, the administration aspects of the course, so you get in some orientation, and then we'll look at, what we will see lecture by lecture, right? So my name is Rahul Mangharam, as you probably know, and so I'm a faculty member both in ESE and in CIS, because our work is kind of spanning both, like, the electrical systems aspects and a lot of the, safety and formal methods and verification aspects in that's more in CIS. We really don't care about departments in this course, because as you'll see, this course is very cross-disciplinary. And so I direct the Safe Autonomous Systems Laboratory in Levine Hall. And I also serve as a Penn Director for a Department of Transportation, National Transportation Center called Mobility 21. And that in that center, we look at a lot of aspects of not just building autonomous vehicles, but autonomous systems in general of, how do we provide, guarantees for safety and performance for any kind of closed loop system. And our work goes from automotive systems to medical devices to energy systems. For this course, we'll just focus on, the AV aspects. So you can reach me. I'll mostly be this semester in the lab. That's Levin 279. My office is right next door to in Levin 272. And there are office hours, and you can reach me. Mostly we'll be communicating over Piazza, not over email, but we'll walk through that too. So this is your saviors, right? So this is our instruction team. So we have Dr. Johannes Betz, and maybe you can give a quick introduction to yourself, Johannes, and then I'll reintroduce you then. Yeah.
Yeah. Hey, Rahul, thank you very much. And hi, everybody. Hi, students, and welcome back to the semester. My name is Johannes, and I'm a researcher, postdoctoral researcher in the field of autonomous driving with a special focus on autonomous racing. So whenever you have any questions about what's going on in autonomous racing, just come to me, ask questions, and we can discuss together. My focus is especially in the field of path planning and control. So when it comes to driving fast, overtaking vehicles, I'm the right guy. So welcome, everybody. I'm looking forward to teach you and looking forward to work with you in this semester.
Yeah, and we have so Johannes is very modest. So he comes from TU Munich, as you can hear from his accent. So he also knows which are the good beers to have and how to enjoy life. But more importantly, he has actually worked in like real racing cars, right? Real racing of autonomous vehicles in the robo race competition. And then his team more recently, and that won the 2019 robo race in Europe, and then his same team from TU Munich won the 2021 Indy autonomous racing competition. And these cars are going at like insane speed, right? 200 kilometers plus, and head-to-head racing. Just last week they were in Vegas, and so these are like, and they won the $1 million prize in the Indy autonomous racing. So anytime you want to borrow money, you know who to call, not me, that guy, right? So I'm just kidding. So and then we have Billy over here, so, and Billy will for sure be your savior in this course, and he has built a lot of the groundwork in this course. But I'll let Billy introduce himself to you.
Hi everyone, I'm Billy. I'm a second-year PhD student in the lab. My research is focused on how to build, test autonomous systems, and then how to basically take a look into agent interactions in autonomous systems. if you have any questions on the software side and the hardware side of the course, um, I'll be glad to answer all the questions since I've developed most of them. So yeah, nice to meet you all.
Yeah, and then we also have Zire. Let me find his.
Yes, I'm here.
Oh, there you are. Okay, good. Let me
Yes,
add you.
I was named anyone Annie before.
Okay.
Hi, everyone.
Yeah, and so Zire actually, so Billy built a lot of this course, Johannes built a lot of this course, and then Zire actually took this course and then helped build, some of the modules, and you'll see him throughout. But he's also a PhD student. But Zire, you can introduce yourself.
Yes, hi everyone. I'm a first-year PhD student in Rahul's lab. So I'll be focusing on the lab administration and reading of the lab work. So if you have any questions for the lab, you can ask me.
Yeah, so find out which good beers to buy and then buy them for Zire because he's grading all your labs. And then, but so Zire's interests are also in like GPU computing and perception, computer vision, and then you'll see more of him in the vision parts, right? So this is our team. You'll get to know all of us really well because we are going to be doing a lot of stuff in hands-on. And hopefully it's safe to do that, but we are really looking forward to that. All right, so the reason, we also have this kind of team and, this course is also like a team effort in many ways because it takes a lot of different skills to build an autonomous vehicle that can both operate at the limit of, performance and also be safe, right? And I'll keep repeating this theme through this lecture, throughout the course. So you'll hear that often because you have to know, like, obviously perception, planning, control. Fine, those are the three building blocks. But then to make the system scale, we will use some machine learning in the latter part of the course because we can't model, like, say, the physics accurately once you start drifting. And we can't necessarily, we want to use different vision and perception algorithms using machine learning, right? And for this course, we'll do a lot of things out of the box. And then, but then you want to race using different reinforcement learning approaches. You're interested in that topic, and that's what you can pick as a project towards the end of the course. And then there's formal methods. Most of you all may not have worked on formal methods, but essentially this is just ways of having logical and mathematical models of these systems to essentially be able to prove the safety under all operating conditions. And so you need to do that in order to provide any kind of guarantees for safety. And then we will be operating on a GPU. It will be pretty transparent to you for most of the course. When we do like certain parts of particle filters or SLAM, those are optimized for the GPUs. And but then later on as a project, you would also be able to accelerate your system to work at a higher performance. Mechatronics, power systems, those are basic building blocks. You need that to build a real AV, but in this course, we have taken that out of your path. But if you want to extend the platform, you can do so, but we want to keep us pretty efficient, but you would need those skills too. And then one skill that is kind of, really not emphasized in the university or in our education as much as this kind of autonomous vehicles brings together a lot of modules, a lot of, software is running in the car. And you need to have some middleware. And that middleware has to be built on top of a real-time operating system. You can't just throw arbitrary kind of Linux and building like a safety critical system. You can't even use a robot operating system or ROS that we will be teaching you the course with in a production grade system, right? So how would you need to have knowledge of that too. So a lot of the unicorns, like Waymo and Zoox, Amazon, or Newtonomy, or a lot of Too Simple, they all have to build a team that has all of this. And ideally, the lead of that team will have many of these skills. And so what, Johannes, Billy, Zire bring are different aspects. They're familiar with many or most of these aspects to different extents, and but they will specialize in different aspects. And our goal is to essentially get you exposed to a lot of that, right? So here are all the links that I shared with you in terms of the course logistics. And everything is basically online. We will centralize it all in Canvas, and but discussions are on Piazza, labs are on GitHub. That, right? There's a link to the course calendar. I recommend you just subscribe to that, and then we will have recorded lectures basically for the whole semester, so you can catch up anytime, revisit the lectures. And because we also don't know how Omicron is going to proceed, so by default we'll always be having a backup of recorded lectures, and then the lectures will be in this playlist right at the bottom over there. That's just a YouTube playlist, and I had today's lecture there too. So once we'll be online essentially till Monday the 24th. Monday the 24th, if everything works out well. Then we'll move to Detkin Lab. And so Detkin Lab is in the Moore building, right at the bottom next to the ENIAC machine. And lectures will start at 3:30. They don't necessarily always have to go till 6:30, but essentially our session plan is that we'll have a lecture for the first 50 minutes, then a tutorial for about 20 minutes or 40 minutes, depending on the type of tutorial. Today's tutorial will be a little longer. And then you have hands-on, right? You work on the simulation part, you work on the real vehicle, you basically do your lab sitting with your partners right over there, because we overlap it with our office hours too. So you can ask us questions, and you'll have hundreds of questions in terms of how do I get this set up. We'll give you all the instructions, it's all documented, but we'll be around, right? So our office hours are basically clubbed into this time over here. So you'll see us, and because of Corona, we just feel like 2 sessions rather than meeting multiple times in the week. So you can also just do other classes, or if you want to stay at home for the other parts, that's up to you, right? So this way we essentially meet for a substantial amount of time, and you don't have to come separately for office hours. So, and again, you can always talk to us at any other time. We can always get onto a quick call, by Google Meet or Zoom or Hangouts or whatever, right? So generally then the course, our general idea, very high level, is first we want to teach you how to learn to drive, right? How to drive the F1TENTH car and simulation and in the real car, and how to first stop crashing, how to basically, just drive with the LiDAR without any maps, and be able to navigate a course. And you may not be doing it very efficiently or high performance, high speed, but at least you're moving, right? So and then the second part, so the first part is about just maybe the quarter of the course. And then the second part is the next, next half of the course, right? So so we are 3/4 of the course by the end of learning to race. And there you basically learn how to now improve on your agility, on your speed, and how do you build on these techniques. So you're focusing on the performance improvement, but you're going to be using a lot of techniques that are map-based, and that are going to use a lot of motion planning techniques to be able to do that, to be able to race and overtake, right? So but that's at the very high level. And so essentially we will introduce you to ways in which how you can first do obstacle avoidance and just navigate a course very, not efficiently, but safely, right? So first you get safe, then you start to build up speed, you follow a racing line, and you have a trajectory, you're following that trajectory, and then eventually you're going to race against other cars. So it's not just about how good your trajectory is, it's also how good the other car is, and how do you outperform that competitor, right? So this is a very competition-centric course. So it's not like, hey, I just do the lab and I go home. No, you do the lab and then you kick ass in the race, right? And that's where the fun is at, right? And everyone's going to have fun doing that, right? So I mean, there is no sort of serious competition, but you'll see teams do get pretty competitive towards the end, but everyone's still friends here, right? So let's walk through, and if you have any questions, please do ask, right? So in this course, we'll start from the ground floor, right? And the ground floor basically just means that you have basic knowledge of linear algebra, and you may be exposed to one or more of these concepts, but we don't expect you to know a lot of that, right? And so we don't have big expectations on what you bring to the course, but what we do have is that you start learning fast, right? So we will start with the basics of Docker and ROS, and you basically get introduced to ROS2. And then your first, assignment is on just understanding ROS2. ROS2 is quite involved, and some of you may be exposed to ROS1, and then you'll say, okay, and you can pick up ROS2 pretty quick. And so this semester we've made the shift to ROS2, and so it is new for us too, right? So and ROS2 is new for pretty much everyone, but I think we have to make that shift eventually, and just better to do it sooner rather than later. Any new kind of vehicle system that is being built in a prototype mode will be most likely using ROS2. Then we'll sort of look at the basics of how to get the car moving, driving safely, and I'll walk you through all these different modules step by step. But essentially, we're going to go from the basics to then simple navigation approaches, and then to higher performance navigation approaches with path planning, and then and model predictive control, and then we'll look at some topics in vision and learning, and then you'll have a hands-on project, right? But for this slide, I just want you to focus on essentially this column that is on the right side, right? So you see that these are the labs, and these labs are all pretty hands-on. It's like saying, okay, you learn some concepts in the lecture, now let's put them in action. And the whole point of the lecture is to support the fact that you have the basics, you know how to go about it, and now you have to execute over there. So there are over 9 labs. So there are basically eight coding labs over here, right? So lab 1 is the intro, but then and it's an individual lab for this week. And then starting from next week, lab 2 essentially will start becoming a group lab. And then you essentially will work as a group lab for lab 2 to lab 8, up to lab 8. Lab 9 is a special lab that's on ethics of autonomous vehicles. And that's a important lab because, and it's very different from just a coding lab, because it gives you some kind of framework to think about, if you're buying an autonomous vehicle and, and you have an accident, then where does the fault lie, or where is the liability? And, who is morally responsible for the actions when the machine is making most of the decisions, but the driver is supposed to be doing something? And then, so where do you point the blame? How do you reason about, fault? And in this kind of regime where decision making is kind of handed off to a machine, but the people who implemented the machine, they say, well, the machine is learning on its own, it's making its decisions. We just initialized it. We just sort of gave it its day 0. So don't blame us, right? So but I think it's important to have a framework as you go about, because it's not just about autonomous vehicles. It's as you build these decision-making systems in general, right? So, and then you'll see that through the course that we will also not have any exams, right? And we'll essentially have 3 races, and I'll come to that shortly. So you'll have to, so we'll all work in teams of 3 students per team, and there are 25 students. So that basically will mean that one team will have 4 students, and but that's fine. Generally, my role has been, and probably you guys have seen that as you work in teams, as the team grows bigger, only like 2 or 3 people maximum do the real work, and someone makes the slides then, right? The 4th person. So don't be that 4th person who's just making the slides. You'll really learn a lot here, right? So So what is important, as I showed you, is that the skill set that you need to have is quite broad, right? So that's why it's important that your team has a mix of majors. Many of you all are from meme or a meme undergrad background. Very few are from EE. Most are from Robo. Very few are from CIS, or maybe leaning towards CIS more, or even if you're Robo, you're more of a programmer than a mechanical person. So we want to have, a team. Ideally, a team would just have, one of each major, right? So if you're 3 robos in one and 3 meme in another, that's not a good idea, right? So ideally also have a mix of geography, right? So I'll just put it explicitly. Like, we don't want people all from the same geographic region to be in one team and all from the other geographic region. So we'll mix them up. And also you want to have a mix of programming expertise. Most people are probably more comfortable with Python, and then a fewer may just have had some real world experience with C++. So you definitely want to have, someone with C++ experience in your team. So you want to fill this skill survey out. And so it's essentially just tiny URL, F1-skills, that, right? And I'll just copy this link over here and paste it in the chat. So you can fill this out while I'm yakking away over here. So essentially this is a very quick survey, and then that will help us assign the teams, right? And if you're not happy with your team, or there's some arch nemesis that you don't want to work with, let us know. That's not a problem. But we are just trying to make sure that the team has good coverage of the skills. All right, so let's get through how are autonomous cars today at a very, very high level, and why do we really care about racing? Seems kind of frivolous, right? I mean, let's build some real serious systems. Why do we want to build racing cars, and that too these RC kind of racing cars? So if you look at the AV, perception, planning, control pipeline, on the left-hand side, you essentially have all the, sensing, right? So you have your RGB, from camera feeds and Lidar feeds, and then you have and then you have, you can capture depth views, you can capture optical flow views of how far things are, how fast things are. Then you do your object detection, object tracking, and then at the end you do semantic segmentation. And then this basically gives you the basis for the perception for a vehicle to begin navigating, right? So, and then as we go through the navigation process, you essentially have, different levels of planners. High level planners, like a mission planner, is like saying, oh, I want to go from Philly to Times Square in Manhattan, New York City. And it's like Google Maps, right? It's just giving you the global plan of that you need to get onto, I-95, and then take I-95 to the George Washington Bridge, and you'll be there, right? So the behavioral planner, on the other hand, says, okay, well, in order to get to I-95, I need to get onto this on-ramp over here. And I need to basically shift from, into the right lane or the left lane. And so it's making these discrete choices. And then the local planner says, okay, fine, you want to get onto this on-ramp. And then the local planner is just planning ahead, maybe 100 milliseconds or 100 meters ahead. And it's just saying, okay, these are the possible trajectories that you can take. These are good trajectories. This is the best one. Let's take that one. And then what your vehicle is doing is just now going to do trajectory tracking. And it's going to essentially generate the sequence for steering and acceleration inputs to follow that path. And this repeats, the sense, plan, act, just repeats, anywhere from 20 to 100 times a second, depending on what system you're using. And so this is an overall general pipeline, right? But let's see how this works, right? This is a video from 2016 in Switzerland. This van is parked, and this Tesla can obviously, there's this van right in front, and it basically goes and taps it, right? So, okay, no big deal. And nobody got hurt, and this is 2016, right? It's early days. And then this is also, I think, 2016, 2017 timeframe. This is in China now. And this car is essentially driving down the highway about 55 miles per hour. It sees a street sweeper, or at least we see the street sweeper. and then the Tesla smashes into it, and basically the 23-year-old dies on the spot. And both are kind of similar. It's a stopped vehicle on the side of the road over there, right? So, and then this is a more recent 2018. This is a Tesla driving on the highway, oversteers here, and then crashes into the wall, right, into the cliffside. And why did it do that? Well, our point is not to pick on Tesla. The only videos that we have are from Tesla, because that's the only car company that is selling vehicles, with this capability or advertising some capability like that. So we're not picking on Tesla. It's a good company to pick on, but our point over here is that, these systems are still far from, being very safe, right? I mean, and these are not like freak cases. These are kind of pretty mundane cases, actually. They're not like, it was a fault of somebody else and they did something wrong and the car couldn't decide fast enough. And these recalls, this is like from June 26th of 2021, so just last year, and just a few months ago. And there are obviously always recalls with like vehicles, but this is a recall with these safety concerns with the autopilot system over here, right? So what does this mean? How do we reason about it? We are not about like, autonomous vehicles are safe or unsafe. You can decide on that, for yourself. And the idea over here is that we want to understand, when these safety issues happen and how do we actually be safe enough, right? So we are always trying to balance safety and performance over here, right? So if you see this video on the top side in this box, this car over here is trying to merge in, and this is a pretty mundane situation. If you drive anywhere, you have to merge in, and this truck is being like a typical Philly driver. Although this is not a video from Philly, I'm not letting the car come in, right? So I whenever I drive, it's just the same. So, but for us, it's a pretty normal thing, and you are trying to figure out, okay, when can I steer in? And eventually you get onto the highway and life goes on, right? But for autonomous technology today, it treats this as a non-cooperative scenario over here. It's really trying to compete for a spot to get onto the highway. And if it is too conservative, it'll just be waiting on the side of the road. If it's too aggressive, it could be the cause of, So you want to basically have a way to smoothly negotiate this merge without delay or hesitation. But the issue with civilian driving is, going back to my case of driving to Manhattan. If I reach Manhattan like 5 minutes late, nobody gives a big deal. They just say, okay, at least you're alive. I mean, nobody really says at least you're alive, but 5 minutes here or there on a long journey is not a big deal, as long as you're safe. So safety is well defined, right? Don't crash and don't cause an accident or even a near accident. But performance in civilian driving, making progress, how long it takes. If you take 1 or 2 minutes to get later to get to a place, that's fine. But in racing, on the other hand, here you can see Alonso and Vettel going at extremely high speeds, right? About 200 kilometers per hour. Very expensive cars coming very close to each other, and they don't know what the other driver is going to do next, and they are still extremely aggressive, right? And this is a totally not a non-cooperative scenario. This is an adversarial scenario, right? And a crash here could be very dangerous and very expensive. So they are now at the level where they have to figure out how to balance safety and performance. And if they're even like half a second too slow, they're out of the top 10. Half a second is top 10, right? That's the spread that you have. And that's a career choice, right? It's not even a choice then. So you have to basically be safe enough, but as fast as possible. So now we have these metrics of safety and performance very well defined. And this balancing this trade-off continuously under different contexts of driving is what we're going to focus on for the rest of this course. That's the focus of a lot of our research also. And this is a slide from Johannes, actually, since he's the racing buff here. And this is essentially just showing that, why we focus on autonomous driving, because we want to look at how do we do all of this at the limits of performance, at the limits of perception, planning, and control. racing is an unstructured environment. You don't have lane markers, you don't have traffic lights, you don't have roundabouts and intersections or stop signs. You just have to go forward as fast as you can, right? Different tracks can have different conditions. And so it's also, you have a lot of uncertainty in terms of how the other driver is going to drive. You all are aiming for the same goal, right? And when I drive in Philly, it's not like everybody wants to get to my house, right? So at least not in Corona times. So I'm not that popular. So you have to figure out, like, what kind of strategy you have above and beyond, your planner, and how you're going to navigate not just this current curve, but the next one. And these decision making have to be at very, very fast reaction times, like that, right? So you also need to know what are the limits of your vehicle's handling, like that. You're not going to just conservatively make a turn. You're going to be drifting, and you're going to see to what extent you can push the vehicle and push the driver. So what you're going to be programming for this course, and mostly towards the end of it, is what goes in the race driver's brain, right? Because you're programming the racing driver's driving policy. So autonomous racing over here has actually exploded in the last couple of years. Obviously, we use F1TENTH, and we focus on the small scale because we can teach that to you. We can't buy you a robo race car, or $1 million robo race car, or a $300,000 Indy Autonomous Challenge. But these are all like really, they're doing amazingly well, right? Robo race was introduced, I think, 3 years ago or so. Super high speed demonstrations of these cars. Indy Autonomous Challenge took that to the next level, where they did head-to-head racing. That means 2 teams against 2 teams. They had a couple of crashes just last week in CES in Vegas. And it's just phenomenal that, in just the last 4 years, autonomous racing has just taken off, and people are really pushing the limits now. And this is, essentially with racing, that's where most of the automotive companies, technology companies, start with their innovations, and then they all trickle down into, our boring Toyota Camrys or Honda Odyssey minivan, and all those technologies eventually come there, right? So let's look at this pipeline now, and essentially we have our sensing on the hardware side, multiple sensors. And so we will have lectures focused just on understanding the sensors and the sensor architectures and how they all come together. And then in the software that's in the middle, again, you will learn in the perception side is basically localization, detection, and also just perception only based navigation, just in terms of like your reactive methods of driving. So you're not making a big plan. You're just saying, okay, I know where people are right now. How do I navigate? But then you want to actually come to planning, where you want to figure out, okay, what's a path to go? How do I behave now when I'm competing with another driver, or when I'm navigating this turn because I need to get in place for the next turn? And how do I actually, generate the right kind of trajectories that minimize my overall cost while adhering to my dynamic system constraints? And then you have, control for both, your velocity and your steering to basically follow a path. And then there are different types of controls. So we'll study PID control, we'll study model predictive control. And then there's the hardware itself, putting all of this together into a vehicle and then making that actually race, right? So that's the general pipeline, but now we'll break it down, right? So this is how it's on the car. There is a Lidar Outfitter on the car. It's a 2D Lidar, and it'll basically provide you, information about where all your obstacles are and where is the free space. Optional cameras are there. So we have many RealSense cameras. You can outfit your car with a RealSense camera if you want to use that for your project. I think we have about 75 RealSense cameras, so please use them because Intel is not using them. And then the car is running a NVIDIA Jetson NX platform, so you'll actually be programming on that car. The nice thing with the Jetson is that you can program directly. You can even connect it to a monitor, and you don't need an external laptop to program it. It's not like a microcontroller platform. You can directly SSH into it. You can directly connect to it over Ethernet, and then just you can treat that as the computer that you're working with, like that, right? So you don't need to have a programming laptop for the NVIDIA board here. There's a power distribution board because there are many voltages, and that's all the nitty-gritty stuff that we've taken care of for you. And it has Wi-Fi on board, and then there's a LiPo battery, which it reminds me that when you get on the hands-on course in the lab, then we'll give you a short tutorial on LiPo safety. That's really, really important. And then there's a standard chassis. This is a Ackerman steering four-wheel drive chassis, and essentially it can go to a max speed of about between 40 to 50 miles per hour. To be honest, we haven't gone 40 to 50 miles per hour. We've gone, I think, about 17 to 18 miles per hour, with autonomous driving, like that, right? So Billy would have done things much faster if he's driving, but that's still pretty fast because the limiting factor is just the size of our corridors, and it's not, the car is very capable, right? So we would love to see teams take this car somewhere in the Penn Park and really push it to the limits. So I'll pause here for any questions. I know there were some questions in the chat. If I'm on the wait list, should I just send me an email if you're on the wait list, and then if there's a slot freed up, then we'll let you know. I mean, I don't want to be the guy who says, oh, there's no space, but the room is the problem. I wish we had got a bigger room, but this is the only lab room that they can give us. If you've already formed your team, just talk to us on and share your team details on Piazza. And again, we want geographic diversity and skill diversity, and and major diversity, which majors you're in. If it doesn't satisfy that, then we'll help you with getting an assigned team then. Yeah. So let's go through the lectures now, and I'll spend about 20 minutes on that, and then we'll switch to the tutorials. So the nice part of this course is that you don't have any exams, no midterm exam, no final exam, but instead you have races, right? You have a race after about in the middle of February, a race at the end of March, and then the race at the end of the semester, right? So this is very exciting because it's competitive. It's not very open-ended. I mean, you have to race the same race that all your friends are doing in the class. So it's not like, come up with a thing, but so it is very competitive, and you'll see that as you race, you become much, much better in both in your intuition and in your coding skills and in your algorithms. And that's what we want, right? So let's start with the AV driving basics in module A. So we have module A, and then B, C, D till G. So I'm going to go through very quickly what we'll cover in each, because you will actually see this, starting from next week. So A is just the intro, right? It brings you all to know how to use ROS and Docker. But then the thing is that before we let you go and race a car, we want you to make sure that you actually build a safe car. You see this car driving to the box, it has to stop before it hits the wall or hits an object over it, right? I'll just play that again. So we'll teach you first how to build a autonomous automatic electronic braking system to prevent the car from crashing. And you'll write a very simple algorithm for that using a metric called time to collision based on braking, right? It's not about how far things are or how about, but it's about a combination of how far and fast the relative speeds are, right? And this is very close to like how real life, autonomous vehicles actually also compute their safety bubble. And you'll work with the Lidar sensor, you'll work with the actual actuation of the vehicle, and you'll also understand failure modes, right? So what if your car works most of the time, but then sometimes, you don't detect things, or sometimes you detect things, but they aren't there. So we'll understand what kind of problems happen with these, when you have false detections or you fail to detect things, and how does this actually turn out in real life too, right? So You will start using from, the next lab, the F1TENTH simulator. This is a snapshot on the right top is the previous version of our simulator. But now this one runs as the F1TENTH gym simulator. And so it's a very scalable simulator. You can have multiple vehicles in it, and it captures vehicle collision, basic vehicle dynamics, and publishes a laser scan odometry. And it's basically built for fast prototyping. What you run in the simulator, the same code directly runs in the car. Right? So the code doesn't know the difference between the car and the simulator. We also have like a fancy simulator. I call that fancy, but and a lot of this Johannes and Billy have put together also is the LG SVL simulator. And so this brings in perception. In the top one, you don't have, besides a LiDAR, you don't have like, camera-based perception or any other sensors. And so here you can have photorealistic worlds like, the F1TENTH racing on a actual racetrack. It's, built in Unity, and it's also going to be running on AWS. So that's important. More important than the fanciness of it, I think, is that you learn to run this in AWS and you basically be able to run all your jobs in the cloud, right? You can launch this from a browser tab, and all of this will work in a browser tab, which is amazing. But it's important that you use the modern machinery of a cloud-based simulator, and it's very sophisticated physics and lots of sensor integration. You can add clouds, rain, change the lighting, and whatnot, right? So it's very very rich environment. For the most part, you'll be using just the F1TENTH gym part. For your projects, you can use the LG SVL simulator. But we'll come to that as a latter part of the course, because we want to introduce you to the LG SVL simulator also. We are super excited about it. So once you sort of have your car and now you want to figure out, okay, now how I'm going to get sensor data. The thing is, like in a real, autonomous car, you have different LiDARs in different places, cameras in different places. The thing is that each sensor is just telling you how it sees the world from its perspective, from its own frame of reference. So how do you get like a combined frame of reference so that from the car's perspective, like that, right? So the first thing that you have to learn in that is, okay, I want to combine all of these perspectives into something that I can say build a bird's eye view of the system, or I can use together with in my sensor fusion algorithms. Is you just have to understand coordinate transform systems, coordinate frames, and then be able to do rigid body transforms for where are the world coordinates and where are the maps. So for some of y'all, this will be a refresher from what you learned in the intro to robotics, but you're going to apply that to the car. You're going to also do that in ROS, and then you'll be doing post transformations in ROS and then using that throughout the semester. So we'll get you started on that over here, right? So for example, you can see this is the view on the left from the LiDAR perspective. And then from the right, you can see the perspective is now in the world frame, right? Which makes a lot more sense now, because on the left, the world is moving, but you're staying in the same place, right? So how do you do this transform from, local or measurement frame to the global frame? Again, this is, basics of getting started, but it's important that we're doing that with this car over here. Then once you get hands-on with the car, we'll give you a tuned up car, but you still have to understand how to do PID control for the speed and PID control for the steering, so that the car is actually, well tuned as you start racing that, right? And so you'll be doing this kind of testing over there for the motor control and tuning. And then you start to say, okay, I want to move the car straight ahead. I want to move it forward. I want to make it do one loop. So we'll start using reactive methods. That's basically just taking the current or the instantaneous sensor inputs and then making a decision on how you're going to drive that, right? So this is one example, is a wall following. It's kind of like what you would have done in high school or in undergrad, like, line following or wall following. So this shows you like our early races, the teams were just basically following like the left wall or the right wall and just going through that. There's no optimized, trajectory or anything, but it works out of the box. It's very simple, but this introduces you to the basics of, PID control, how to compute the error, how to understand the failure modes. And you'll actually get to then, figure out that for real, right? So you can see how this PID, the different gains and what are the impact on getting the car to say essentially drive, smoother and straighter manner as you desire, right? So that's important because we are moving away now from this perfect simulation world into the real world. So you need to just have a car that actually steers according to the way you expect it should steer and goes at the speed that you expect it to go. Then you will understand how to do obstacle avoidance. Now that you can drive straight in a clear track, how can you drive straight in a track that's littered with obstacles, right? So as this car is driving through, we have a lot of obstacles in its way. And how does it just navigate? The car does not know any map. We are showing you the map of this, but the car does not know that. The car is just seeing, hey, there's an obstacle there, there's an obstacle there. And what's a heuristic kind of algorithm to go about doing this, right? And so this is called the follow the gap. Basically just saying, okay, wherever there's open space, let's go there. But there are lots of nuances into how you work with that. And then you will implement that in simulation and then in the car. And you can see this car is able to navigate through all these obstacles. And again, it's not a high performance system, but it's pretty agile. And this is right outside our lab and it works well. In fact, this video was made by a sophomore, an undergrad, and he actually helped write this lab. You can see his picture there, Dhruv Karthik. He actually right now works in Apple on the autonomous driving team, which and he's really enjoying it there. And then we come to this part, right? This is race 1. And essentially you can see that now you're just going to be using reactive methods. That means, and then you're just going to drive a single car as fast as possible around the track. And this is an example video from the F1TENTH Grand Prix in 2018 in Portugal. And essentially you will have to complete 5 laps without crashing. If you crash against a wall, against any obstacle, then you basically get a penalty for that, right? So, and that's your race 1. Okay, any questions so far with that? Okay, so feel free to speak up anytime, right? So then we'll look at mapping and localization. Okay, if I have a map, I can definitely drive faster, but let's see how that works, right? So at the core of all these mapping and localization algorithms is something called scan matching, right? And that's basically saying, okay, I'm here right now and I moved. And so how do I know, how much I moved based on 2 snapshots that I have? And so I want to register these 2 snapshots to figure out how to do that. So how much did I move with respect to the previous snapshot? And so we'll look at this algorithm called the iterative closest point algorithm. And that basically you'll read a research paper and then you'll implement that. In all of our opinions, this is a little painful lab, but it's you're not going to directly necessarily use scan matching, for the rest of the course, but you'll have to implement it to get an idea of what happens under the hood in these simultaneous localization and mapping algorithms, right? And so you'll understand the math behind it, and you'll actually implement this for real. And although it may not be as efficient as some of the publicly production grade SLAM algorithms that are out there, they all use scan matching. And so I still insisted with our team that we keep it in. You can tell us how frustrated you get with this lab, but it's a good lab that provides you this foundation. So you're not just like using some GitHub repo and just downloading it and running it on the car. You also know what's happening under the hood. Then you basically will do what I just said. You will download this Google Cartographer SLAM package and essentially run that. And the SLAM package works out of the box, and you'll also install it and run it in the corridors. You'll build maps with cartographers and then race the car along that track, right? So, and this gives you hands-on experience with running SLAM and a high-speed car. And then you learn the basics of, okay, now you have a map and you're getting multiple sensor observations. How do you know what's the pose of your robot and where are you in this map? Right, so you'll use a particle filter, you'll implement this particle filter, understand how it works, which is basically a version of Bayesian filtering. And then you'll run this particle filter to localize yourself in the real world. Okay, great. That's very nice, right? Now you have a map and you know where you are on the map. Then you need to figure out, okay, how do I drive? And you want to pick a set of waypoints, and the simplest way is called pure pursuit, right? So basically pick a set of waypoints to make a reference trajectory, then track that trajectory as you keep localizing yourself, track the next point, and then the next point from that, right? So and so we'll basically show you how to implement and run a pure pursuit, and both on the simulator and then in the car. Then you see the fun starts, right? I'll put the audio on here also.
Right here is 5 meters per second. It's a really fast spin velocity.
So that's So that's basically actually one of the previous TAs, Jack Harkins, who is running behind this car and getting a workout at 2 o'clock in the morning. Don't feel bad for him. He's making lots of money and really enjoying himself in NVIDIA now following this experience. But the car is moving much, much faster, right? Because it's not just doing reactive stuff. It knows where it is in the map, and it can drive much more confidently. And you're going to use that in your race 2 now. And so this is a car that's using a map-based method to drive through this. And again, you can see now the car is much faster, much more confident, and actually navigating this very skillfully. You can plan around a racing line and so on, right? So, and then we get to, okay, planning around a racing line, right? How do you figure out now different algorithms for, global planning and then local planning? And so, and how do you combine these capabilities of these map-based methods while being agile and adaptive to obstacles that are not necessarily known on the map a priori? How do you navigate around that, right? So how do you understand and we'll help you understand like search-based motion planning, probabilistic planning methods, RRT and variance. That's a rapidly exploding random trees, right? So you'll implement that once again, first on the simulator. Basically our mantra is, if it doesn't work on the simulator, forget about it. You're not going to touch the car. And then if it works on the simulator, it may work in the real car. And so then we'll look at like global planning approaches, based on occupancy grid and planning in the discrete space and continuous space. And so this is like a refresher for planning algorithms, but very focused on how you can put them to use in a racing context. And then you will have an intro to model predictive control, because that's going to help you generate these trajectories that you can see in red, green, and blue, and pick the green trajectory, which it feels is the best trajectory out of the possible trajectories, and then help you actually drive very confidently and also very precisely as you're racing. And then we get to vision. And so I think now vision and special topics are all, beyond the basics of racing, right? So, but so we'll have 2 lectures, one on basically, classic computer vision approaches. So detection, pose estimation, using classic computer vision, that's also understanding how to detect lane markers and then to drive within lanes and race in a 2-lane racing track. And then, so that's just with the camera only, right? So because a LiDAR is actually as expensive as all the other parts put together, right? The LiDAR is about $1,700 for the cheapest LiDAR. And the rest of the car is about $1,500 retail, right? So if you just have a camera only car, that just brings down the whole cost of the car a lot lower, right? So you'll understand, multi-view geometry and then stereo vision, and then how to apply, like say, object detection, applying tiny YOLO to detect the car, and then to have a fast enough detection pipeline with that, right? So and then you can apply these skills now to, like, say, reinforcement learning, like imitation learning. You drive the car, around a lap 2 or 3 times. And now you see the error is quite small when the car starts to drive on its own. And this is the car driving on its own, and it's just showing you what is the input steering versus the predicted steering angle of the car. So you can use RL as a project option down the line if that's what you want to do, right? And then you get to the end of the course, that's the Grand Prix, right? And that's essentially a head-to-head racing. And now you see that there's a vehicle in front of this car, and these both of them are very aggressive. It almost hits the other car, comes close by, and then so essentially it's both of their missions are to win, right? So, and you can see it that it almost hits the car once, then I think it hits the car again, recovers very fast, continues to race, right? So you're going to put all of these things together, no crashing, or you get penalized for crashing, but then you'll have two cars racing head to head. And then you have your final projects, right? I'll let you take a look at all of these. There are many different options you can choose, across perception, planning, control. You can propose some, we'll suggest many, and you'll do this project in the last month of the course. So all through April. And this is where you push the limits of what we have taught you so far. The labs are essentially the building blocks to get you to race, but then, you're interested in some kind of, most people are interested in some flavor of machine learning for this, or for planning or control or perception. Sure, we are very open to that, and we'll support everything to make sure that, you get the most out of this course. I just want to end with a note on, the nice part of us getting back in person, hopefully, is that we actually host a lot of competitions with F1TENTH. The videos I showed you are from the second race of F1TENTH or the third race. This year, we're going to have the 10th F1TENTH Grand Prix, and we've had many of these in different conferences. You can see in ICRA, in IROS, IFAC. This slide still needs to be updated with a lot of the conferences from last year also. So this is an example of a conference. I'll just put the audio on so you can watch it for 2 minutes.
National University of Science and Technology. Technical University in Prague. The University of Virginia. Drive, race, perception, planning, control. Do you have what it takes to be the best autonomous driver?
So that was from 2018 when our algorithms were much simpler, but you can see everyone's having a lot of fun. The nice part is that the ICRA International Conference for Robotics and Automation 2022 is going to be in Philly. So we don't have to travel anywhere, and you guys can actually race in this competition, right? It's going to be in the latter part of May after the semester ends. So the timing is perfect, right? So don't make travel plans yet, right? So, and the nice part is that we will be hosting this, the 10th autonomous racing competition is going to be a flagship competition over there. In addition, what Johannes and the team have organized over here is a workshop and this is a second workshop on opportunities and challenges for autonomous racing, which will also be at ICRA. And last year we had, professors and actual racers, people building this from MIT, Stanford, Georgia Tech, EPFL, ETH. And then we have already a confirmed list of speakers who all work in this area of autonomous racing. And so it's a super exciting workshop, and everyone is invited to that too. And then because it's local and and essentially Penn is hosting ICRA this year, right? So that's an opportunity. So that's why it's important to work hard through the semester so you can actually race in this race against the teams and top teams in the world, right? And the winner makes big bucks. No, I don't know how much the winner makes, but it's I think the thrill is really in the chase, right? So so the other aspect is that all the students that participate in F1TENTH over the years, and this obviously should go on like 2020 till 2022, but all of these students in the past, they've all gone on to get onto their dream jobs, right? In Tesla, who's in Tesla, Parel over here, he's a senior path planning engineer there. NVIDIA Autonomous Systems, Honda Autonomous Systems, Amazon Robotics, and so on. And the idea is that this hopefully helps you also get onto that kind of career path if that's what you'd want. And we are here to help you with that. So that ends the intro lecture over here. And essentially you are going to be programming this car to be the best autonomous driver. And I wish you luck and welcome on board. So I'll stop over here and also stop the recording at this point, and then we can take any questions. And then maybe what we'll do is also start to take some folks an intro for everybody, and then we'll also do an intro in person. Okay, so we'll let's just start.